All right, our next reaction is oxymercuration, and we're going to see this is very similar to acid-catalyzed hydration. In this reaction, again, we're going to start with an alkene. This is an alkene addition reaction, and we're going to take an alkene to form an alcohol. So just like the acid-catalyzed hydration reaction, we're going to break the pi bond of the double bond. We're going to be adding an H and an OH across the double bond, following Markovnikov's rule, okay? But the key difference here is that there are no rearrangements that take place with this reaction, all right? No rearrangements, right? So a scenario on how you differentiate these two reactions is if we took this alkene here, right? So if we use the acid-catalyzed hydration reaction, we know that that's going to undergo a rearrangement, right, to form an alcohol. But in this reaction, if we take the same starting material, right, in step 1, we treat it with mercury acetate, HgOAc2 in water, followed by step 2, NaBH4. Now we're not going to have the rearrangement take place, so we will form the alcohol at the original sp2 hybridized carbon that is more substituted. All right, so if you think of our reactions as basically tools in a toolbox to build new molecules, the acid-catalyzed hydration, right, will form this tertiary alcohol, whereas oxymercuration will not have a rearrangement and form that secondary alcohol, right? So we may want to form the product and form the tertiary alcohol here, but we also may not want to do that, where we don't have a rearrangement. So this is an example on where you would use the acid-catalyzed hydration or use oxymercuration. All right, so the first thing, let's investigate our reagents here. First thing we should notice is that this is a two-step process. We have step 1 and step 2, okay? It's important that we separate the two steps. So what this means is you take your alcohol, you add mercury acetate and water, you run the reaction, you work it up, you get a product. Then you take that product, treat it with sodium borohydride, run the reaction, and then you get the final product. So you have to include your numbers here. You've got to include your numbers, all right? And just one thing to point out, when you have two-step reactions, you can also use a semicolon to separate the two steps. So you could take mercury acetate in water and then use a semicolon to say we're next treating it with sodium borohydride. Okay, so a semicolon basically means that we have step 1 followed by step 2. All right, so just a note for further reactions as we're looking if they're multi-step. So let's again break this down. Mercury acetate, HgOAc2. What does that structure actually look like? Well, that has a mercury atom connected to an acetate. So an acetate is an O, C double bond O, CH3, and obviously we have two of those, O, C double bond O, CH3. So that's what an acetate group is. An OAC is equal to an O, C double bond O to a CH3, right? But it's fine to just abbreviate it as OAC, all right? So again, in this reaction, you can see, right, in the top example, we're going to be adding an OH to the more substituted position, right? So there's an H here originally. That H is still there. We've now added the H and we've added the OH following Markovnikov's rule. Same example for the second here. There's the more substituted carbon, right? So again, we're going to be adding this OH to the more substituted carbon to get that product, all right? So that's basically the reaction, all right? To understand why, there are no rearrangements, we really have to look at the mechanism of how this reaction works. All right, so let me clean this up a little bit, and then let's work through the mechanism to understand why there aren't any rearrangements in this case. And what you're going to find is that we're going to be forming a carbocation, but that carbocation is going to be stabilized. All right. So I'll take this example. We know that can rearrange but doesn't. So we'll treat this with step 1, HgOAC2 in water. Okay, and sometimes you could see a co-solvent here. You might sometimes see a co-solvent of THF. Okay, step 2 is sodium borohydride, NaBH4. And we know the product we're going to get out here already. We add the OH to the Markovnikov position, no rearrangements. All right, so let's look at this mechanism. The first thing we're going to see is that when you have HgOAC, right, this is an equilibrium where one of these ACOs fall off, right? So you can basically break this mercury acetate bond to get an ACO minus plus an HgOAC plus, all right? So that mercury now has a plus charge, right? Because this has a plus charge, that mercury is going to want to form a bond. We can think of this as our electrophile, all right? We know that the pi bond, right, these electrons are nucleophilic, right? They want to attack something, and that's what happens here in our first step. The pi bond is going to break and attack the mercury. Okay, so we are going to attack the mercury. And this leads to an interesting situation here. Where do we add the mercury, right? So we can add the mercury to the end carbon, HgOAC, which gives us a secondary carbocation. But why does that not rearrange? All right. Mercury is interesting because it is a transition metal and it has access to electrons in its d orbital. So even though I'm not drawing lone pairs on here, the mercury does have lone pairs, but we just don't normally draw them for inorganic species. All right, there's like hidden lone pairs in there. So it turns out we can draw resonance structures or alternate structures where the electrons that the mercury have can support this and in fact actually form a bond to that carbon. So this mercury can take some of those d electrons that are hidden and physically form a bond to both carbons. Thereby the mercury now has a positive charge. Okay? The other thing we can see here is that the mercury can also form a bond to the other carbon. So the mercury could just be bound to that carbon, leaving you with a carbocation there. All right? So this is sort of the key intermediate, the key resonance structure, where the mercury is sharing the burden of this positive charge, right? This is the key structure, why we don't have a rearrangement. So even though you have a carbocation here, we can have the structure where we now have a positive charge on the mercury. And that's what prevents the rearrangement. This prevents, or really stops, a rearrangement from occurring. Okay, so the mercury the double bond will attack the mercury. You'll form these species. Okay, so we sort of have these three structures. All right. And then what's going to happen is, remember, we still have our water molecule in our first step. And in fact, that water molecule is now going to act as a nucleophile and attack the more stable carbocation. All right, it's not going to attack the mercury. It's not going to attack the least stable carbocation. It will attack the more stable carbocation. So let's draw that product over here. Right, so if we draw our arrows, that will attack. That means our mercury is out on the carbon at the end, HGOAC, and we now have a new bond to O. That oxygen had 2 bonds to H and 2 lone pairs, but one of the lone pairs became this bond. That oxygen now has a positive charge because it only has 5 valence electrons. All right, and as we've seen before, we can take another water molecule, or you could even take your acetate anion. Right, we just need a lone pair. This lone pair or one of these lone pairs can take this H away, right? We can deprotonate that hydrogen, okay, leaving us with the first product that we see, where we have an alcohol at that position and we still have our mercury, our HGOAC. So this is in fact the product that is formed and isolated after step 1. After step 1. It's our alcohol, but we still have our mercury attached. All right? But as we know, this is a 2-step reaction, right? A 2-step reaction where we treat this with sodium borohydride. So in step 2 here, when we add sodium borohydride, NaBH4, all that does is it inserts into this bond. So NaBH4 will replace that mercury with a hydrogen. Okay, so if you look like we've had 2 hydrogens on here originally, we've now added our third hydrogen, right? Our third hydrogen has come from our sodium borohydride, replacing the mercury. All right, and that's the mechanism of this reaction, right? We attack, deprotonate, and then replace the mercury with a hydrogen to get our final product. Right, so here I've drawn in the H's, but our final product will really look like this. All right, that's the final product that's formed in this reaction. All right. So I want to kind of talk about part B of this reaction. So if you notice here, we have another, again, sort of an oxymercuration. This time, though, we're going to take an alkene and we're going to form the functional group called an ether. Going to break the pi bond, add an H, but this time we're adding an OR. Again, we still have no rearrangements. What's different, instead of adding water as our solvent and our nucleophile, we're now going to be adding some alcohol, like methanol or ethanol. All right, so if you look in the mechanism here, right, when you have water, water acts as our solvent, but it also acts as our nucleophile. Water is our nucleophile. So in the bottom example, instead of having water here, you're going to have the exact same mechanism, but methanol or ethanol is going to attack. Right, that will attack here. Right, so instead of having an O with 2 H's, you're going to have an O with 1 H and 1 Me or ET. So as you deprotonate, you lose the H, but you still now have your Me. So what you notice here is when you add MEOH, right, we don't get OH, we get OME. And if I add ETOH, I get my OET. All right? So this reaction, you really have to pay attention to the reagents. Mercury is your huge hint, right, that we're doing an oxymercuration. But if the solvent we use is water, excuse me, we get an OH, HOH, OH. If we use methanol, MEOH, we lose the H, we get an OME, again, carbon to the O. If we use ETOH, we get our OET, still following the rules. All right, so this is really two reactions. It's really one reaction, and we just have to pay close attention to our solvent. We can use water to get out alcohols, or we can use alcohols to form ethers.